Let's do a problem from start to finish. And remember, really everything in differential equations, that's not true, but most things in differential equations can be thought of as harmonic oscillators, at least in this introductory course. So we're going to go back to our harmonic oscillator. This is, if you remember, the general form for a damped harmonic oscillator, or really an undamped harmonic oscillator too. Just B will be equal to 0 if it's undamped. So suppose that we're looking at a damped harmonic oscillator with a mass of 1 unit, a spring constant of 2 units, and a damping coefficient of 2 times the square root of 2. All right? We're going to get some practice with radicals here. So we have a damped harmonic oscillator with these parameters. Then, of course, our system, or our differential equation, our second order differential equation, looks like this. Again, oh gosh. No, it doesn't. It does not look like that. I did not write these in the same order as they appear in the equation. Again, mass of 1, damping coefficient 2 root 2, spring constant 2. We have a second order differential equation, which we can always write as a first order differential equation. Every second order differential equation can be written as a system of first order differential equations by just saying, all right, let's call y dot equal to velocity. Then what does y double dot equal? Y double dot is going to be negative 2 times y minus 2 root 2 times y dot, which again we said was v. And we can transform this into a system. We get dy dt equals 0, 1, negative 2 root 2 times y, which is just y comma v. So that is our system here. It's kind of weird having a 0 right here, but no problem. Don't be tricked, by the way. This is not partially decoupled. Triangular matrices are partially decoupled, but even though you can sort of see a triangle here, this is not a triangular matrix. Triangular matrices have to do with the diagonals of the matrix, and specifically, this is the diagonal of a matrix. Nobody really cares about this, as far as I know. But anyway, this is what we're dealing with here. To solve this, what are we going to need? We're going to need eigenvalues. We're going to try to find those straight line solutions. Find those straight line solutions, we can do a lot of things. Straight line solutions will be when the rate of change, and again, this is the rate of change, because A times V, sorry, we should be really careful about using the letter V, but we will. V is velocity, the vector V is a potential eigenvector. And again, let's call this matrix A. This is just A times the position. So we're looking for something like this. We get non-trivial solutions when the determinant of A minus lambda I is equal to 0. Let's find out what that is. A minus lambda I looks like this. Well, this looks fun. We need this to equal 0. This will give us our characteristic polynomial. When we do that, we're going to get, multiply these two things. You're going to get 2 root 2 lambda plus lambda squared minus a negative 2. Whew. Well, this is fun. Let me make sure I'm doing this right. Negative lambda times this. You just distribute the lambda, negative lambda, you get 2 root 2 times lambda plus lambda squared. All right, we need this to equal 0. Okay, quadratic formula it is. Or you could complete the square if you wanted to. I love completing the square. But it might be a little odd here. Let's try it. What happens if we try to complete the square? We get lambda squared plus 2 root 2 lambda. This is probably going to be a terrible idea, but I'm just a little curious. And then that's going to equal negative 2. To complete the square, you have to divide this by 2 and then square it. If we divide this by 2, we get root 2. Squaring it is 2. So we add 2 to both sides. Wait a minute. This is very silly, right? We just undid. So this is already a perfect square. sort of. All right, this is going to be lambda plus the square root of 2 squared equals 0. So lambda plus, right, lambda plus square root of 2 is equal to plus or minus the square root of 0, which is 0. Lambda is negative square root of 2. That was funny. That one got me good. We found our eigenvalue. Quadratic formula would also work. I think completing the square doesn't get enough of a chance. This is so much nicer to me than the quadratic formula. I don't want to do the quadratic formula here. Quadratic formula with a radical coefficient? That sounds gross. Completing the square is cool. Okay, so we have our eigenvalue. We could find an eigenvector, but we don't need to. We know the general solution. The general solution, we said, was just going to be, well, let's check our notes. E to the lambda t times our initial condition, which we were not given one, plus t e to the lambda t times v1. And v1 was just a minus lambda I times that initial condition. So we have e to the lambda t times initial condition plus t e to the lambda t times v1. We don't know v1 yet. Let's find it. Or maybe before we do, I'll write it down the formula. Right? It's a minus lambda I times v naught. What do we already know about this system, which shouldn't surprise us if we're talking about a damped harmonic oscillator? It's a sink. 0, 0 is a sink, which again should not be surprising if we have some kind of spring and it's damped. Yeah, it's approaching 0, 0. It's approaching not moving. Imagine if our spring just like woo, 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 woo. It just goes nuts, right? Of course, our eigenvalue is negative. If our eigenvalue weren't negative, we would have alarm bells going off in our head. And that's one of the advantages to whenever you're working with some kind of physical model, is you know kind of what needs to happen. And anytime you see mathematically something else, you know you made a mistake. Anyway, how do we find this eigenvalue? Oh, sorry, it may or may not be an eigenvalue. Depends on if it's 0. Remember, this is always an eigenvalue or 0. And if this is 0, our initial condition is the eigenvalue. Okay, so then what we have here is, what is our matrix A? It was not very nice. But A minus lambda I, V naught is just going to be, not X naught, Y naught. Whew, gosh. It's going to be Y naught, V naught. This is terrible notation. This is the initial condition V naught. And this is the initial velocity. Should probably have changed some of these letters, but they're still different. One has an arrow. All right, what was A minus lambda I? Let's copy down what A was. 0, 1, negative 2, negative 2 root 2. So A minus lambda times I is the matrix, and then we're just subtracting negative square root of 2. So we're just adding root 2 to the diagonals. So this becomes root 2. Negative 2 root 2 plus root 2 is negative 1 root 2. And again, everything off the diagonals never changes here. And all we have to do to find out what this is just multiply. It's not pretty, but we can. This is root 2 y naught plus v naught. And the other one's negative 2 y naught minus root 2 v naught. Again, this is not a pretty eigenvalue. Sorry, eigenvector. But it is an eigenvector as long as it's not 0. And whether it's 0, well, that just depends on y naught and v naught. I'm pretty sure it would be pretty hard for this to be 0. So we have our general solution. Hooray! We did it. What is our general solution? It's going to be y of t equals e to the negative root 2t times v naught, which again is just the initial position and the initial velocity, plus t times e to the negative root 2t times our initial times our eigenvector, rather, which is root 2 y naught plus v naught negative 2 y naught minus root 2 v naught, like so. And I haven't been looking at my notes at all, so I'm going to quickly check to make sure that we do have the right answer. Hey, neat. I didn't make a mistake. So what would this look like if we did some qualitative analysis? All right, well, let's give you an initial condition for actual qualitative analysis. So let's take this over to the next page. Suppose our initial position was equal to, I don't know, 1 unit. And our initial velocity was negative root 2. Wait, I actually don't think I want to do that. I don't actually want to do this at all. Let's just do some qualitative analysis just like this. Okay. All right, so there's going to be some eigenvector, and we don't know the direction. You know, I will give it to you. Suppose our initial condition is just going to be 1, 1. So we're starting 1 unit away from equilibrium, and we're also moving 1 unit per unit time, also away from the equilibrium. And again, here, if we're creating our phase portrait, this is normally x comma y, but our x is now our position y, and our y is now our velocity v. Okay? Remember to always label your axes. Remember what your variables represent. Well, if this is our initial condition, then what does our solution look like? Then our solution looks like y of t equals e to the negative root 2t times 1 comma 1 plus t e to the negative root t. Oh yeah, I definitely am regretting this, making this up already. 1 comma 1, this is root 2 plus 1. And this is negative 2 minus root 2. And this is our eigenvalue, our eigenvector. So our eigenvector represents our straight line solutions. What does this actually look like? This is about 2.4. Square root of 2 is about 1.4. So this is about 2.4. And this is again also 1.4. So this is negative 3.4, if my math is correct, roughly. So it's roughly at 2 comma negative 3. Okay, our it's like this. This is our straight line solution. And again, remember, lambda is negative. So we're going towards the equilibrium. We have a source. Remember what our solutions look like. They're going to be looking like this, kind of. All right? But again, we know our initial condition as well. Our initial condition is 1 comma 1. So we're initially starting right here. So we know we could find our initial direction vector by plugging into our original equation. If we have 1 comma 1, I'm really getting away from myself right now. I don't actually want you to do this much by hand, but I've kind of came up with an idea and I have to finish it. So if we're starting at 1 comma 1, what direction do we start moving? Right? Because I know we're going to eventually approach along the tangent line, but I don't know whether we're approaching from which direction. Okay, so if we're starting off at 1 comma 1, then our initial direction, right? Our initial direction is just going to be multiplying this times 1 comma 1, 0 plus 1, and then negative 2 minus 2 root 2. So we're going to be going right and down. So that tells us we're going to be approaching like this. And then again, if we wanted to draw like other solutions with other initial conditions would be like this. You know, they're all swirling around. Let's look at what this direction field actually looks like. Again, finding the general solution right here is really what I wanted you to get out of this. Could you find the general solution? And I want to do some qualitative analysis, but again, I didn't really have a well-formulated question, so it's a bit hard for you to work with that. But anyway, what we have right here is for our general thing. Let's forget about initial conditions real quick. What was our system? 0, so it's just like 1 times y. It's actually v, but in the calculator it's written as y. And then negative 2x minus 2 root 2y times x minus 2 times the square root of 2 times y. And this is what we have. So I said if we started at 1 comma 1, oh no, it's here. Let me make it so you can see. If we started at 1 comma 1, it's starting right here. Hey, look, it has negative time plotted. We don't need to include negative time. I think there's an option for that somewhere. But yeah, it just approaches along that straight line solution, exactly as we said, right? If you start at the dot and go down, it's exactly what we thought would happen. Cool. You can see the straight line solution too, right? If you approach here, you're going to go up along the straight line solution up. All right, if you're right here, you're going to approach. All right, I didn't draw it straight. It was supposed to be straight. But yeah, we have the straight line solution going that way too. And again, you could see lots. And as time goes on, we're approaching along the eigenvector. If we did have negative time, right, they would end up like swirling kind of parallel. But anyway, or actually I don't disregard that last part. But yeah, they're all approaching because we have a sink. They're all approaching tangent to our line of straight line solutions. That's it for this video. We'll end it here, and then that's pretty much actually the end of repeated eigenvalues as well. The last two videos are relatively painless, I think. Well, one of the last two videos is relatively painless, and we talk about what happens if we have 0 eigenvalues. Bye-bye.